Welcome everyone to another CP Top Call. This is call number 159. It's my pleasure to introduce Dr. Tejesh Bundy. Dr. Bundy is an associate professor of physics and astronomy at the University of Alabama, where his work brings fundamental physics, precision time, and advanced engineering. His research focuses on atomic clocks, resilient navigation systems, precision synchronization, and next generation positioning and timing technology. Over the last 15 years, he has worked in organizations including ESA, NASA, ISRO, and he is the founder of the Quantime Laboratory, where his team explores quantum timing, resilient GNSS alternatives, AI-based PNT systems, and deep space navigation using pulsars. Dr. Bundy is also deeply involved in the precision timing community. He's a senior member of IEEE, has chaired multiple sessions for Institute of Navigation Precise Time and Time Interval, PTTI, conference. Also serves as a program chair for the ION PTTI 27, and is a steering committee member at the ATIS WSTS conference. Today's talk, Atomic Clocks as Precision Time Source, will explore the technology that underpin modern precision time infrastructure, from microwave and optical atomic clocks to emerging quantum clock systems used in telecommunication, GNSS, scientific research, and deep space missions. Please join me in welcoming Dr. Tajesh.
Thank you so much, Ahmed. And I'm happy to be here amongst all of you and give this talk today. As the title suggests, atomic clocks as precision timing sources. What I would like to have you as a takeaway message from this particular talk is to understand that the atomic clocks are silent workhorses, and many of the applications that we know of as of today is really dependent on the atomic clocks. So that is something hopefully I'll be able to, excite you for understanding, how these clocks work and what are the kinds of atomic clocks. Are there, whenever we say atomic clock, is it one particular type? And what are the different kinds of atomic clocks that are there? And why do we really need those many kinds of atomic clocks? And also I'll touch upon the applications part of all these atomic clocks. And finally, I'll talk about the research aspects that we are doing at the Quantime Lab. And briefly, I'll also touch upon the ACCEPT program, that is an NSF NRT program that is to train students in precision timing. So with this, the outline of my talk is as follows. So it gives, sorry, just a second. Okay. So it gives at first we'll talk about the time measurement as an art evolution. That means it's as much as it is science today, measuring time and the methods that we use to measure time is equally an art as it is science, right? So I want to touch upon that and explain about how this really evolved in terms of how we measure time over a few thousands of years, dating back to 3,000 years. And then I'll touch upon what is a clock, and then we'll see a very brief idea of what is an atomic clock, and then I'll give an overview of the types of atomic clocks that are present around the world. And we'll also touch upon the everyday applications, as I mentioned before, GNSS systems overview, and the highlights of the Quantime Lab research. So, starting, way back in 3000 BC, in the Stonehenge, the way the stones were kind of arranged, it gives us an idea that our ancestors wanted to know the idea of the shadow of the sun using these stones. And that's how they kind of split the day into Okay, this is morning when the shadow is on one side, and then when there is very little shadow, then it is kind of noon, and then the shadow on the other side gives you an idea that the length of the shadow gives you an idea that, okay, now it is going to get dark, and therefore, and then there's a very long night, right? So as you can see, the time was not equally divided into equal intervals, right? So as we move along to 1700s and so on, there are various you know uh, places in Europe where you can see such tower clocks. And on the right hand side here, I give the precision or stability in seconds over one day. So that the tower clocks were accurate down to 15 seconds, sorry, 15 minutes over a day, for example. And then the Huygens pendulum, it would vary by 10 seconds, plus minus 10 seconds over a day. The marine chronometers, and this was essential in 1750 when Harrison invented the marine chronometer. It was very much necessary in order to navigate, um, to find different sea routes, to go from one point to the other, and so on. So that is accurate down to plus minus 1 second over a day. And then in 1920s to 30s, we started measuring the Earth's rotation. If you haven't seen it, this is really fascinating to look at some of the very old telescopes. These are equatorial telescopes, which means somebody would almost, I mean, as close as you are to the equator, you would have to literally lie down to observe a particular star in the night. And, you see the cross wires from this telescope, how many ticks does it take for it to cross a particular star in the night sky? And with that, they know what is the speed of rotation of Earth, and based on that, we were managing time down to millisecond over a day. And then the invention of quartz oscillators in 1930s brought a significant and a remarkable change, I must say, uh, with the time accuracies coming down to microseconds. And late in 1950s, the atomic clocks were game changers in terms of how accurately, how precisely we can actually measure time. That means in the whole process, if you see as an art evolution, as I call it, to really see how, um, you know, how many parts that we can measure in terms of the seconds as we count, right? So the finer you can dissect a second, the better is your precision and stability, right? So today, the best of the optical clocks, it's not the lattice clock. In fact, we have actually moved on from the lattice clock to the aluminum quantum logic clock that varies by plus minus 1 second over 30 billion years, or even better than that, which means, as we know, the age of the universe itself is 14.6 billion years. So the best of the clocks that we have today would vary by plus minus 1 second over twice the age of the universe. That is a remarkable achievement. And therefore, among all the other parameters that we are able to measure, I mean, in terms of the physical parameters, time and the time intervals, we have been able to measure much more accurately. Okay. So here are the oscillating frequencies. I mean, most of you clearly know about all these things. The pendulum, 1 hertz, one oscillation per second. So all I want to highlight with this slide is the higher the frequency, better the time resolution. But the resonance width and the quality factor matters. The signal to noise is an important aspect. And the problem of counting, that means higher the transition frequency, you got to be able to count that as well. So in that sense, here is a very simple idea behind what we call as a clock, right? So there is an oscillator, and we must be able to count those oscillations as accurately as possible. And that's what, as a combination, you would call that as a clock, right? Now, in that sense, everything is an oscillator, like even the Earth rotating, the solar system going around the sun. So everything oscillates in the universe, but some of them make better oscillators. So here is a resonance curve, which gives an idea that at a particular frequency, giving a certain amplitude, the line width is an important parameter. And here F naught is the frequency at which that oscillator is oscillating. With this, we get the quality factor Q, which gives the resonant frequency divided by the line width. That means if your signal is sharp, then it is a good oscillator. So in essence, the clock counts oscillations of stable signal. The better or the sharper the signal, better is the oscillator, and more precisely, the time can be measured because time is inverse of the frequency. So here is a pictorial representation of what is an atomic clock. The idea here is you somehow need to hold the atoms in a confined region of space. It could be to hold the atoms in a glass envelope, or to have the atoms in vapor phase in the vacuum chambers and so on. Then, if you have a macroscopic oscillator, let's say this macroscopic oscillator, typically it would oscillate at 5 megahertz or 10 megahertz, then you multiply the frequency in order to match the atomic resonance frequency. Okay? Then the atoms would respond to such an interrogation that you give. And what you get as an output is the spectroscopic signal. So the spectroscopic signal would look like the curve that I showed in the last slide, right? Then the idea is to the peak of that curve, you servo loop and lock the macroscopic oscillator. By doing so, we adjust and maintain the frequency of this macroscopic oscillator to a reference atomic transition frequency. Then, if you look at the stability of the macroscopic oscillator, it is derived from the atoms directly. And this is the basic idea and the principle behind what is an atomic clock. So here I want to explain a couple of other kinds of clocks before we touch upon looking at what are the kinds present around the world. So here's a simple idea of a microwave atomic clock. A cesium clock is what I've taken. Let's say there's a cesium source, and when you heat the cesium source, it dispenses the cesium atoms as output. There, in the ground state energy of cesium-133 atoms, say for example, the ground state splitting is 9.1 gigahertz. So that means between these two states, you can call that as whenever in the excited state means the atom is in the spin up state, and in the ground state, the atom is in the spin down state. Okay. So with these two states, when the atoms are passed through the state selector, the magnetic state selector, you can choose only one kind of spin state. And then you pass it through the microwave cavity, where the first zone gives you a kick, gives the kick to an atom to as pi over 2 pulse. And then the atoms are allowed to process freely from lower state to the excited state, let's say. And after a certain time, or in this case, you can also say the free evolution happens with the spatially separated two microwave pulse zones. So after a certain time, then another pi over 2 pulse is given. So with this, what happens is it behaves like an interferometer. So what you end up getting is the Ramsey fringes, the interference between the two pi over 2 pulses, and that's what you detect in the detector. It's not the ion detection, but it's more a generic scheme. But in this case, it is really the cesium atoms in one particular state what you detect. Then the signal processing is done, and the feedback control loop is put back to the cavity in order to get a much more stable output in terms of the counting. So this is how the microwave atomic clocks work. And as an example here, I've given the cesium clock. Note here, this is very easy to understand. In this case, the cesium atoms are hot atoms. If you were to use lasers in order to cool the hot atoms down to microkelvin regime, because at the room temperature, the atoms are few hundreds of meters per second. That is the kind of velocity the atoms are at. But when you use lasers in order to cool these atoms, you can reduce their velocity down to few centimeter per second. And this is exactly what is done in laser-cooled cesium fountain clocks. So once the atoms are cooled, again, they're passed through the 2 pi over 2 pulses, and they're detected. By this method, you can have much better stabilities, right? So this analogy here gives you the cesium beam clock, as well as when you laser cool the atoms and pass it through the microwave cavity, time separated microwave cavity, you can get much better signals with laser cooled atoms. Now, let's also have an idea of how an optical atomic clock work, or in general they're just called as optical clocks. So let's say, as an example, I've taken strontium lattice clock here. In this case, the atoms are laser cooled, and the idea is, with this laser cooling, the atoms are slowed down, and therefore they're able to be trapped either in 1D or a three-dimensional trap, where there's a laser trapping potential that is created. Within that, when the atoms are trapped, they're confined to a specific region of space. And then these atoms can be interrogated, which means these atoms are isolated from rest of the atmosphere, right? So the more well you isolate these atoms, the better is the stability. So in this case, in the strontium lattice clock, you would laser cool the atoms and then trap in the optical lattice. Then the interrogation is done. For the strontium lattice clock, for example, the atomic transition is 429 terahertz or 698 nanometers, right? Then the fluorescence of that signal is detected. The signal processing is done. Now, in this case, the atoms are oscillating at the optical frequencies. So we don't have any electronic counters in order to count the number of oscillations very precisely. As I told in the very beginning, a clock means, you have the oscillations, which are happening in the first part, and you got to be able to count them very precisely as well. And that's where the optical frequency comms, come into play. 2005 onwards, the invent of optical frequency comms made all the difference. And from that point on, the optical clocks became a reality. So here, the fluorescence output signal that we get is having a certain frequency, let's say, 429 terahertz. Now, the optical frequency comms will have equidistant comb lines. The clock signal that comes out is then very close to any one of the comb teeth, let's say. Then the beat frequency between them will be in the microwave regime. So that is how you're able to then use your electronics in order to count the oscillations, and generate the feedback mechanism to close the clock loop. So the key difference is the microwave clocks are in tens of gigahertz, whereas the optical clocks are 10 raised to 3 to 10 raised to 5 times higher frequency. Therefore, if you recall, higher the number of oscillations or higher the frequency, better is your time resolution. So that's the key idea here. Now, the laboratory-based atomic clocks, cesium fountain clock, the laser cooling is done at the lower part here, and then the atoms are launched through one end of the cavity up in space here, and this is a vacuum chamber. And when they free fall, they go through another end of the cavity. So that's how the 2 pi/2 pulses are interrogated. And finally, the atoms are detected in what particular um, state these atoms are. Now, with the very first cesium fountain, NIST F4, these are all pulsed cesium fountains, which means the atoms are prepared, launched, and the final signal is detected. And again, the atoms are prepared, launched. So this, say, for example, every 10 to 15 seconds, one particular operation is done. Whereas for the fountain clocks that were developed at Swiss, they wanted to ensure that these atoms are continuously moving and therefore the signals are possible to be detected every second. The only reason why this is done with the fountain clocks is to avoid the light shift effect. So when you're detecting the atoms, you don't want any other light fields. And also when the atoms are freely evolving, um, in the free precision mode, you don't want the extraneous light to impact the energy transitions. And that is what we call as a light shift effect. So to avoid that, the fountains are run in pulsed mode, whereas in the METAS, continuous wave fountain, they found a way how to trap these light, but just allow the atoms to pass through. It's a very brilliant mechanism, although it's pretty hard to run it continuously. So here are some more cesium beam clocks as well as the cesium fountains at PTB Germany. Strontium lattice clock that I spoke to you about. This was the previous best clock until the aluminum clock took over, just like 8 to 9 months ago or so. And then the ytterbium ion clock. So the idea here is that when you take an atom, obviously these atoms are neutral in nature, and you strip off one of the electrons, then it becomes an ion. When it is ion, you can trap these ions in the electric potential. Generally, what we call that as a Paul trap or penning trap. Uh, Penning is by the magnetic method, Paul is by the electric field oscillation method. So then you can actually trap these ions. Even a single ion can be trapped. And then you do the same laser interrogation with this ion, see what is the performance and how these atoms would respond to give you the atomic resonance signal, and then utilize that resonance signal in order to lock the macroscopic oscillator, right? So here's the aluminum ion clock, or quantum logic clock. This is done in a very brilliant way, that the laser cooling is done mostly to aluminum as well as the magnesium ions. So the idea here is the atoms which are of interest are undisturbed because we use another set of ions in order to extract the information out of that. So in that sense, the perturbation that we induce is reduced by one order of magnitude. And that's how they're able to achieve the world's best clock stability down to 2.4 10 minus 19 level. That's impressive. So here are some of the commercial atomic clocks, the ground-based um, cesium, rubidium cell clock here. Again, rubidium cell clock, and this is also rubidium cell clock. What I want to highlight with this is most of all these clocks work based on the lamp. Um, there is a rubidium lamp, which means there is no laser in order to excite these atoms. They use rubidium lamp, and with that, a certain filtering technique is done between the two isotopes of rubidium, rubidium 87 and 85. The energy transitions are very close by, and therefore one can use rubidium 87 cell in order to produce the plasma, and then the light that comes out of that would have two frequencies, or essentially two frequencies. And then you can use another filter cell in order to suppress one of the frequency light output. And thereby you have kind of a very benign, monochromatic light output, kind of a laser, let's say. Not quite, but you do get a single frequency. That's the idea. With that, you can do the excitation of the atoms, and uh, then inside a cavity with the rubidium, it works at 6.8 gigahertz of oscillation. Then the response is seen on a photodetector. And again, that signal is then utilized to lock the macroscopic oscillator. So that's how the rubidium clocks work. Cesium beam clocks, we already spoke about. That is one of oscilloquartz, and very recent, microchip updated cesium beam clock. And passive hydrogen masers. These are some of the compact, but at the same time, high performing clocks. And these are again the cell based clocks. In that sense, if you want to look at the frequency and the stability, I'll get to that in a minute. What do I mean by frequency, stability, and all that? So, if you look at very long term stability, cesium beam clocks would do much better, because it's not the same atoms that we are using every time. So once you prepare the state, you detect the atoms, and those atoms are then gone, right? So you use another set of atoms, and that's how the beam clock works. Whereas with the rubidium cell clock as well as the passive hydrogen maser, um, in both these cases, you have the same set of atoms confined in a glass envelope, in order to excite and get the signal out of that. So in that sense, there are wall collisions, and due to that, the long-term performance of the clock is kind of limited. So here is the active hydrogen maser, which is perhaps the best ground-based clock that we know of. And this is manufactured here in Tuscaloosa, just 5 miles from my lab here. It's wonderful to see their facility very close by. So the space clocks, rubidium cell clock, again, as I explained, the key idea of how a rubidium cell clock work is still the same, but you got to have different considerations when these clocks need to work up in space. I'll get to that in a minute now. And then here is the accelerators, which is on board the GPS, and also frequency electronics. These clocks are also on board GPS. Passive hydrogen maser. Initially, it was developed by SpectraTime, now Saffron. Um, and the industry which is manufacturing these for Galileo navigation program is Leonardo in Italy. So these are the best space clocks for the GNSS system that we know of, which is on board the Galileo navigation system. And then test flight was done with the Deep Space Atomic Clock, which was developed and built by NASA JPL. Perhaps the best space clock that has ever been tested so far. Going forward, in the Galileo program, they are planning to move towards the optical clocks. And in that sense, the optical iodine clock would be one of the candidates to be up in space. They have already done some test flights with a mission called Compasso. So based on all the previous studies, they're gearing up towards a better or shorter form factor of the optical iodine clock. Because the key parameters when you want to go to space is size, weight, power, right? Um, Now, there are a few other requirements for the space clocks that one has to carefully consider when designing and developing a clock. So, a space clock, obviously, you need to think of the swap, and reliability is extremely crucial. And to a certain extent, you got to have proven space heritage. If, say, for example, the clock itself does not have the proven space heritage, it takes many years with multiple missions in order to get there. But at least one has to use the parts which have had the proven space heritage previously. And the thermal design, as I mentioned, for the space clock versus the ground clock is very different from each other. And the mechanical robustness is very crucial because the clock has to sustain the launch vibrations. Digital design becomes very important because if you want to make any little changes when once the clocks are up in space, you would be able to send certain commands in order to say make some small changes. So therefore, digital design is very important. Radiation hardened design, obviously, because it has to sustain all the space radiation and the harsh environment up in space. Telemetries, this is the only way that you will know how these clocks are behaving in terms of their health parameters. And therefore, you need to have as many telemetries as possible. And it's not only the clock on board a particular spacecraft, right? So there are various other subsystems and payloads on one particular spacecraft. Therefore, these clocks need to sustain a certain level of electromagnetic interference, and shielding is very much necessary to avoid any unwanted magnetic effects. So a thorough characterization of all these clock parameters and long-term ground tests are essential, both independent of each component and then the standalone test of the clock itself. And when once it is integrated with the spacecraft. So it's a very rigorous program when you want to build a space clock. So I highlighted to you about some of the optical clocks, and until last couple of years all these optical clocks were confined to laboratory space. So now the idea is to be able to move them from one lab to the other. And because in order to know how good a particular clock is, the only way you will know how good a clock or an oscillator is when you can test with another oscillator. And in order to precisely know independently how that oscillator is behaving, you need a third one, right? So unless you have really good clock, at least an order of magnitude, better clock, and then you're testing another clock which is not so good, then only two will suffice. But if you have identical clocks, minimum of three is needed. So here is the, and that's why I'm calling it as transportable optical clock rather than portable. Um, so here is Toptica, Germany are preparing ytterbium ion clock. One can actually order all these clocks. They're not ready off the shelf, but they can build you one if interested. Strontium ion clock by the SLS USA, and strontium lattice clock by Riken Japan. And they were the first to announce that they can one can order these clocks, but you can look at the price point. They're in millions. So here is the Nest ytterbium lattice clock, which is in a more advanced stage at this as of now. So pretty soon, they will have their clocks that can be moved out of the lab as well. So here are a couple of few portable clocks. That means they're rack mountable and therefore you can actually move from one point to the other. Acetylene clock by Besant, iodine clock, rubidium 2-photon by inflection, and there's also another rubidium 2-photon by Quantix Australia. So the key difference between these two rubidium 2-photon clock is the very first one, inflection, is a single color 2-photon clock, whereas the Quantix, they're using two lasers, and therefore it is two-color 2-photon clock in order to be able to have better control over a perturbing factor called light shift effect. So I probably need to really move fast. There's quite a lot, many slides. I'll kind of skim through, and if you have more questions, we can always come back to those particular slides, and I'll be happy to address. Okay, so here I'm highlighting the chip scale atomic clocks. So they Hopcroft London used this chip scale clock, and they built a clock that one can buy with almost 60 times the cost of the actual chip scale clock. So many other companies are developing chip scale clocks. So when it comes to the systematic bias as well as the statistical fluctuations, here in this analogy, many of you are probably very well aware of this. That is, if you take a shooting target and if you shoot multiple bullets onto that. So in the first instance, it is neither stable. That means, all these bullets are not grouped very close by, and they're neither accurate. That means not close to the center of the target, right? So the closer you are to the center of the target, that means that determines your epsilon here, the systematic bias. And the statistical fluctuations over time, y of t, gives you how bunched these different bullets are, right? So down below here, we see the frequency, how it varies over time, which gives you y of t. And how close you are to this zero line gives you the idea of the accuracy, okay? So in the second case, it is not accurate, but it is stable, or you can call that as it's precise. In the third, it is wiggling around the zero line, that is the reference line. So therefore it is accurate, but it is not precise. And whereas the last one, it is both accurate as well as precise. So which means this is a much better clock. So in order to evaluate, how all these different clocks behave, we use a tool called Allen deviation. So in that, when you compare the two clocks, what you get is this variation of the frequency, okay? So that can be divided into different intervals of time. So here tau is the variable, which is like 1 second, 10 seconds, 100 seconds, 1 day, and so on. So if you were to make these into smaller chunks of different tau values, and by taking the average of how this variation is happening at each tau, then you can compute at varying tau values using this formula here, right? So once you compute like this, you know at 1 second how your oscillator or a clock is behaving, and 100 and so on. If you were to compute that for different kinds of clocks that we just saw now, say for cesium beam clock, you see it goes pretty well with very little drift or almost negligible, right? Whereas the other clocks, for example, the active hydrogen maser, it's an impressive clock up to 10 raised to 5 seconds, little more than 1 day. And then it starts to drift a little bit. That's because of the collision that I mentioned inside a confined glass envelope. So this gives us how each clock is behaving at different averaging times. So here is another comparison of the high-end microwave clocks and low swap microwave clocks, and also the optical clocks. So we can see that optical clocks are clearly 2 to 3 orders of magnitude better. Now I come to the applications part. So the definition in the SI system itself since 1967 is using the cesium ground state transition. That is, 9192631770 oscillations. When once these many oscillations happen, that's what we call as one tick, that is 1 second, right? So in order to maintain the universal coordinated time, there are the the clocks that are highly contributing are cesium clocks and hydrogen masers. Of course, there are cesium fountains as well, and there are also few passive hydrogen masers. And very recently, they have added a couple of optical clocks as well. So the idea of the universal coordinated time is to take the weighted average of various number of clocks around the world from 53 countries, right? About 590 clocks around the world. So they're all contributing to a place called BIPM, where they take the weighted average of all these clocks. So the idea how this UTC is maintained, and therefore how each other lab would know how far they stand in terms of their own time locally with reference to UTC. This is done through the time transfer, either by common view of the GPS time transfer, or you can also do two-way time transfer techniques with the selected satellite antennas, right? So this is how we define the world time as UTC. The one thing to highlight here is that after 2019, they understood that the SI second really underpins the rest of the dimensional metrology, because we know to measure time much more accurately, as I mentioned, than any other physical parameter as of now. So therefore, many other units are all derived out of second as the base unit since 2019. And because this definition was done in 1967 based on the cesium atom, now we have much better optical standards. And therefore, the redefinition of the time, there are multiple committees which are working on this in order to redefine the second. And that is nearing. In few years from now, we will have redefinition of the second. So here I highlight basically the difference between the UTC and the UT1. When you take the ensemble of all these atomic clocks and make a weighted average of all that, you call that as TAI, Time Atomic International, right, which is in French. And so when you compare it with the Earth's rotation, there is a discrepancy between the two. That's because the Earth day is about 2 milliseconds longer than the daily sum of 86,400 seconds as measured by very precise atomic clocks. And therefore, about every 18 months or so since 1972, we have added 1 extra second to UTC. And this is what we call as leap second. But now there's a new problem. The Earth is not slowing down, but the rotation is speeding up. And therefore, we may not be able to add the leap second. So how can we subtract? We have never done that before. So, one can look into this particular paper by Judah Levine. He explains all that beautifully. So applications GNSS, we saw the space clocks. And by the way, when we talk about GNSS, it's not just the space clocks up in space. You got to maintain the ground segment as well, in which you have the hydrogen masers, you have the cesium clocks as ensemble in order to maintain the ground time. And therefore, every 12 hours or so, the space clocks are synchronized and disciplined again using the best of the ground clock. So it's a closed system, if you can think of. Telecommunication synchronization, I'll very quickly highlight all these applications, okay? Power grid synchronization is very much necessary. Timekeeping, as I explained now. VLBI. This is fantastic. If we did not have pretty good atomic clocks, such as active hydrogen masers, those are the kind of clocks that are used in VLBI, very large baseline interferometry. And the idea here is, these telescopes are quite far apart, but if you can synchronize them and observe the deep space at the same time, that means, you're having a much bigger eye, an eye as big as the Earth. So bigger the eye, better the resolution, and therefore, you know, uh, you can have fantastic images like this of the black hole. So even in such high-end scientific missions, atomic clocks are extremely crucial. Aviation, accurate predictions of the weather, earthquake real-time monitoring, which is already an implemented thing in Japan, the cyclone monitoring, atmospheric humidity analysis, and so on, and the high synchronization of high-speed internet, precise science experiments, such as the one that I explained of the black hole now, and also to measure the speed of neutrinos. Um, so there also you need very precise timing. And then, there are various, many more applications of the military uses. Um, Time synchronization for data centers. So the idea here is we use the GNSS receivers. With that, we get the time stamping. And based on that, you can do the PTP and NTP for the data centers. But in order to have some backup in case of, in case if the GNSS fails, then you got to have an atomic clock as a backup for the data centers. So because these data centers are huge and, it requires enormous amount of power in order to maintain. So therefore, for cloud computing, networking, synchronization, it's very important to have precise timing. Um, Here I highlight one another application where if you have multiple receivers, right, in order to have the phase synchronization between multiple receivers and then perform the fusion of all these signals that you receive in order to, let's say in this case, a radar, right? So there also, you definitely need accurate time in order to phase synchronize the signals that you receive from different receivers. The autonomous vehicles, I'll touch upon that in a minute. And then, drone applications and so on, the timing is important. The key is if you want to know your position, you need accurate time. Here is another example where the self-driving cars, for example, it's not just the signals that you receive from the satellites. That is, not just the GNSS satellites, but you also need secondary sources to be able to give you proper timing. And therefore, I can say that there is increasing quantum demands going forward. Here's a very simple principle. Many of you would be aware of it. I'm not going to go very deep into it, but just highlight that we all know from our high school days, velocity is equal to distance by time. So therefore, velocity of light is very well known. And when it when it traverses from one medium to the other, depending upon the refractive index, you know how much is the velocity of light, and therefore that can be computed very accurately. And therefore, the accuracy of your distance that you want to know really depends on how accurate your time is. And so ideally, we solve four variables. We need to solve for four variables. Therefore, you need a minimum of signal from four different satellites, and preferably widespread in the sky, right? So here is then you accurately compute the distance between uh, the receiver and the signal that you're receiving from the satellite. And here is how it is done. So you have the receiver, which has a local oscillator or a local clock, and the satellite timestamps the signal when it transmits. The antenna receives it. Then you would do the cross correlation between the code that you have of the, it's a replica of the signal that you receive from the satellites. And when they both coincide, then you know what was the time difference between the time stamped and the received time. So if you know the time difference, with that you can compute the pseudo range, the range between your receiver point and the satellite. So by doing so, from four different satellites, you can solve four different variables: X, Y, Z, and time. And so with that, your precise position as well as precise time. So here is a highlight of different kinds of atomic clocks that are used in various navigation satellite systems. A GPS, they very briefly used cesium clocks, but mostly they have transitioned to rubidium. GLONASS, they are still using the cesium clocks, whereas Galileo, as I mentioned, they use both rubidium as well as very high performing passive hydrogen masers. QZSS is a regional system. They use only rubidium, whereas China, they use the rubidium clocks as well, indigenously developed and as well as. So at ISRO, they use similar clocks that were there in Galileo. And also, I was lucky enough to be part of a wonderful team that I led to build the India's first space clock, which is up uh, on India's Navik satellite now and operating pretty well, I'm told. So, and very recently, this was 1023, because this is the sacrosanct frequency that we use in GNSS, and therefore, August 23rd is aptly named as GNSS Day. So, me and a few of my students, we celebrated the GNSS Day to highlight here. And here's the highlight of different global navigation satellite systems, whereas Navik of India and QZSS are regional systems. So the key highlight here is they're all MEO orbiting satellites, except Compass of China. They have MEO, GEO, as well as their satellites on IGSO. And the typical number of satellites that are shown here. So in essence, if you were to just get your signals from any particular point on Earth at any given point in time, out of all these 35 or 31 GPS satellites, you get anywhere from 8 to 11 satellite signals. That is plenty in order to know your position down to 3 meters or so. All right. So I think there's a typo here. Pardon me on that. The hydrogen masers are not there in GPS. This is wrong. Here, I'm not really sure. And this is correct. Okay. All right. And here also rubidium. I know that they tried rubidium very initially, but it was not a success. So they moved on to cesium clocks. Um, all right. So having said that, GNSS is really the base of most of the applications because if you want to know the time at any position on the Earth, we use GNSS as a solid baseline in order to transmit time and or transfer time and for all time synchronization purposes for power grid synchronization telecom and everything that I mentioned. As most of all these applications we use GNSS receivers because time is easily available and anywhere on earth without having to have any wired connections, so to speak. But, however, the GNSS threats are true. And because these signals are weak, there is interference. Space weather might affect these satellites, and therefore, um, there is serious obstruction to the signals that we receive, and also in the cities with high skyscrapers, the signals are obstructed, and any reflected signals are not good to know your position accurately. There is therefore the problem of multipath, and the signals are weak, as I mentioned. And the most important, and this is happening in real time as we speak, the jamming of GNSS or GPS signals. This is happening as well as the spoofing because one can steal. The ships have been redirected in order to go from, rather than reaching the destinations, the ships have been hijacked by the method of spoofing. So you can look that up on Google. There are plenty of news articles on that. So therefore, I think alternative and resilient solutions are needed, and um, it's not a smart idea to put all eggs in one basket, which means not to have another, GNSS as a solution, but to have different timing systems like broadcast positioning system or a telecom with 6G should also go with precision timing embedded into those signals, in my opinion. The sensor fusion, LEO PNT will be a game changer, but at the same time, again, you're relying on similar technology, but with a slightly stronger strength of the signals, right? But we need multiple different solutions in order to have a resilient, timing system going forward. Well, now I come to probably I'll take 5 to 8 minutes if that is okay, Ahmed.
Yeah, yeah, we have this is getting recorded, and we have a lot of calls where they spill over.
Oh, okay. All right, because now that I've come to this part and I have few slides which I want to cover,
Yeah,
and
yeah,
until
please take
now,
your time.
yeah,
Like, and whoever
all
can
right,
stay, they're more than welcome, and whoever has to leave, they can leave and they can watch the recording later.
yeah, as I said, max 10 minutes. Okay,
No,
all
it's a
right,
gem.
yeah,
Go for it.
thank you. Okay, so in the quantime lab and as Ahmed mentioned, is it quantum or quantime or time, so I kind of combined these two words as quantum and time because the clocks, as you all saw, the signals of the clocks really come from the atoms themselves, and there is a clear quantum mechanics in play. And the time that we derive from the atomic clocks is definitely uh, quantime, right? So that's the name of the lab. So highlighting here, what we do in my lab is the lasers, pulsars, and masers. So these are the three key aspects that we cover because many other oscillators will come inside these oscillators, right? So we investigate basic quantum physics and precision metrology principles to develop, niche timing, frequency, and navigation tools. So I want to highlight some of the projects that we are doing in the lab. So we are working on precision timescales, optical atomic clocks, and mostly the portable optical clocks, and that too, a certain uh, physics aspects in terms of how to solve certain perturbing effects in order to improve these clocks stability over longer period of time, and we are working on that. I'll come to that in a minute. And then quantum metrology to understand how these atoms behave for varying physical parameters and so on. Safe GNSS, which means how to understand the spoofing and avoid spoofing, right? So that's an interesting topic that we also work on. And then the synchronization schemes. So how do we do it? We have well-trained students in PNTF research through the ACCEPT program, as well as there are ACCEPT is for the graduate level, student education in precision timing. But um, I even started something called as T squared C squared Tight Timing Clock Club, where we give the hands-on experience for undergraduate students in the lab, and therefore we have this well-trained students doing PNTF research. PNT is a very commonly called notated thing, and many are familiar of that is positioning, navigation, and timing. But I think frequency is the basis of everything. I hope and believe that in this talk I have touched upon that everything starts with oscillation, right? And therefore frequency is the basis. Although and eventually we do, I mean, we get time out of that, and then we do positioning. And when once we start moving, that becomes navigation. So in essence, it should be, FTPN. All right. Okay. So and excellent team of collaborators, and also there are a lot of industrial collaborations and government labs that we collaborate with. So here is one of the highlight, the precision timescale for research and training purposes. Most of the metrology labs around the world, when they are national metrology labs, they need to maintain the time for the nation. And therefore, when once it is given as a service, they are not allowed to fiddle around with their ensemble. So here, when I say ensemble, what it means is that if you have different kinds of clocks and even multiple clocks of similar kind, we combine the signals of these clocks and formulate something called as a paper clock. And then when we see an ensemble output of all these clocks, even if one of the clocks is misbehaving, let's say, then we reduce the weightage on that particular clock. And therefore, overall, your time scale is not very much disturbed. That is the idea of why the clocks are ensembled. And but in this case, we have two active hydrogen measures. We will be adding another one as a third active hydrogen measure to this story. And we have five cesium beam clocks. So we combine these clocks to make an ensemble. Whereas the result, what I show here, is an old result. At that time, we only had three cesium clocks or so. But we developed some of the algorithms in order to, try out different weighting methods and Kalman filter methods and so on. And there are a few papers on this. But as I said, here the idea is to develop new kind of algorithms, use this as a test bed for trying out such algorithms and how it really works with the ensemble and so on. So we have also distributed the time within UA and also outside. So this is mainly, service-oriented work that we did. And we gave the name for this particular IP for internet as rolltime.ua.edu. It's easier to remember a name than an IP. So with that, anybody can synchronize their, like for example, a computer clock to rolltime.ua.edu from anywhere else in the world, which is indirectly linked to our ensemble of atomic clocks. So therefore, You can synchronize your clocks as well. And very recently, we synchronized our tower clock called Denny chimes. So with this, essentially using the PTP method, and therefore the accuracy that we have measured is better than 100 microseconds at any point in time. Um, Now, as I mentioned, the optical clock studies, we do two photon. We have tried both the single color as well as, two color is what we want to do. So in order to reduce the light shift perturbation, to improve the long-term performances of such optical clocks, because these are, as you saw among all the other kinds of optical clocks, um, the the vector atomic iodine clock as well as the two photon clock, these are having much better form factors. So if we can have better long-term stabilities, then these could be much better optical clocks in the field. So that's what interests us. And Dr. Brian Simon and Catherine, our graduate student, working on this particular clock. So recently, I'm not highlighting most of the results here. Recently, we have seen that it is possible to use the magnetic compensation method in order to suppress the light shift effect. So we're working on that. Um, and as I mentioned, the uh, pulsars are spinning neutron stars. Most of the pulsars that we see, which what we are able to observe from Earth, are the ones within our solar system. And the signals are rather weak, and therefore the radio telescopes are the ones which pick up these signals. And from last 20 years or so, there are a couple of fantastic consortiums around the world who have been collecting this data of all these pulsars, but their aim was to detect the gravitational waves in space. Whenever there is a merger of, let's say, black holes, and that creates the ripple in space time. And therefore, they're able to measure these variations affecting the pulses from these pulsars, right? So that they have been able to detect. So you see, the reason why they were collecting the data of all these pulsars was to understand if there are gravitational waves, right? But we saw that this is a great opportunity for us to be able to study these pulsars for timing purposes and therefore for deep space navigation, right? So we started this, all these studies about 3.5 years ago. And we have also published a few papers on that already. Here's the thing. These are some of the chosen pulsars. The stability of these that you can see around 1 year on the x-axis here, it's not in seconds, but in years. It's a 1 year, you get the stabilities down to 2 10 - 14 levels. And whereas these are the best performing space clocks, the deep space atomic clock and the rubidium clocks on board the GPS satellites, we don't have these clock data for much longer periods. And even if they are, we are synchronizing these clocks from the ground clocks, right? So therefore, if you were to look at these pulsars, no one is really synchronizing these pulsars. They are just on their own, and they've been there from thousands of years, and most likely they will survive for 1,000 more years or so. So we can definitely rely on them for deep space, timing and navigation, especially the lunar navigation coming into play. I think to utilize pulsars in one or the other way would be very important. So what we did is to develop an algorithm to do the pulsar ensemble. So to using these different kind of pulsar data, we formulated an ensemble of all that, and the ensemble definitely behaves even better. So over a 10-year time period, you have the stabilities down to um, 6 or 7 10 - 16 level, which is impressive. And therefore, they have the potential. Now, as I mentioned, we need alternative solutions to GNSS. With NIST, we collaborated on doing certain measurements with a few of my students under the ACCEPT program. So there's this antenna on top of the Lookout Mountain in Golden. This basically gives off the signals. This is Fox Network, I think, the channel, KWGN. So the signals, the ATSC 3.0, these are the digital signals, and the signal strength is fantastic when it comes to the television signals, right? And it's not easy to jam. And because these signals operate at multiple frequency bands, it's neither easy to spoof. So, in that sense, they're very robust signals. And uh, the for these ATSC 3.0 digital signals, the timing information was embedded. And so what we did, uh, we used the BPS receiver, broadcast positioning service receivers, and went around multiple locations, about 17 locations in and around Boulder and Denver area, and picked up these signals and measured against the GNSS receiver, with which we knew that, okay, this was a precise position for the GNSS receiver. And how does the timing of the signals that we receive from this antenna compare with that of the GNSS timing? And what we measured um, is that the time variation over about at each location we measured for a minimum of 20 minutes. And we saw that over that period of time, the variation was less than 3 to 5 nanoseconds, which was important. And it's impressive to see that these signals, not only that the signal strength is good, but we also got pretty good. So with that, because there is only a single antenna, right? So instead of that being like a transmitter, think of it that it's a reverse problem of GPS. Because we measured at multiple locations, we were able to compute in order to know the position of the antenna itself. So with that, we got the antenna distance down to 3.38 meters, because the locally the NBS had already measured what was the accurate position of that antenna. So with that, we got about 4 meters of error with our measurements, which is pretty good. Another research in collaboration with JPL. This is to use the machine learning based approach for estimation of the stability of hydrogen masers. In this case, we generically call that as high precision clocks. But the idea here is to use the telemetry of all telemetry signals of the hydrogen maser, and then use that telemetry, train the machine learning model to be able to predict its frequency stability. Okay. So I'm only going to highlight a couple of things, but if someone is interested, please look at this paper that got published only a couple of weeks ago. So as you can see in this plot, the dynamic Allen deviation over different time periods, it behaves differently, which means definitely there are certain things happening within the clock, and we can compute and understand what is the source of these variations. So we did this as two different kind of model. oscillator-specific model and oscillator-agnostic model. In the oscillator-specific model, we choose one of the hydrogen measure, let's say oscillator A, use the telemetry data. We did the training using three different algorithms. And then we use another chunk of that data for as a test data. So, and then we evaluated, how the predicted versus the actual performance of the stability is. And with the oscillator agnostic model, say ABC, three different kinds of clock data was used in order to train our models. And then an unknown clock telemetry signals were given in order to predict its performance. So we we noted that the hydrogen measures, this is the method that we used, only use the internal telemetries to predict the dynamic variations of the frequency stability. The best performing model for us was a convolution neural network, deep learning model. And we also used, random forest and elastic net essentially means, linear regression model. So with that, we were able to get pretty good confidence level up to 75%. Imagine that you have just a single hydrogen maser clock. You have no idea how the stability of that clock is, right? So with our method, one can estimate, what is the stability of their clock, even if it is a single clock. All right. So another exciting project that we're working on is to overcome the challenges of laser cooling in an evacuated atomic cell. Bob is working on his PhD thesis on this. So the idea is it's not easy to, laser cool in a compact sealed vapor cell clock. Because you need much bigger, vacuum chambers, and you need to maintain very high vacuum and so on. So there have been recent works done using the grating methods in Professor Ree's group at UK. So we are investigating into these methods as well to laser cool rubidium atoms in a sealed vapor cell. Another method is to stabilize the laser using the machine learning methods in order to overcome the long-term laser instabilities in terms of the laser mode hops. This is also the work in progress. So we have this laser. With that, we get the pound rubber Hall signal and lock the laser. And presently, we are collecting data for what are the variations due to temperature, humidity, pressure, and vibration, and few other physical parameters that would impact the laser instability and laser mode hop. So with this, I'm sorry I took slightly more time than what was allotted. There was so much to tell. So as a conclusion and prospects, I can say to highlight that the atomic clocks are precise and stable sources for useful everyday applications that the dependence is only increasing. Different clocks are used appropriately as per the application, and currently GNSS is the baseline for time transfer and dissemination, and definitely we need to move uh, toward alternate and resilient time dissemination solutions as well. And I highlighted some of the research activities that are going on in my lab. With this, I really appreciate it, and thank you for your attention.
Thank you very much,
If you
Rajesh.
have any questions.
Yeah,
Thank you.
thank you very much. And no need to apology. Like, thank you for all this, for your extra time and giving us more what we expected. All right.
Wonderful.
So let's open the floor for questions. Okay, perhaps I can start with one. So,
Yeah.
when we speak about the redefinition of the second, we're mainly speaking about like, let's say, the method that we are going to find out, like for the time, basically recreating that interval or like, some whatever it's around to basically create the same like 9.192631770 and a bunch of more zeros in the back, right? Like we're not going to change that. I mean, if you look at the numerics,
Mm.
like the first nine digits are gonna stay the same. Is that the case?
No, 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 it won't be. Um, so the reason for those particular digits to start off with, 9.1 and so on, that's
Mhm.
because we choose cesium-133 as the reference atom.
Sure.
Okay. So it's really that oscillation happening within the cesium atom. And now we are moving away for strontium clock, ytterbium clocks, aluminum clocks, and few other different kinds of optical clocks, right? So
Sure.
therefore, there are two methods that the community has been discussing. One, should we mathematically compute taking the weightage on different kinds of clocks and then define that as a theoretical number, right? So that is one approach. Another approach is to choose any other species. That means the frequency will change. Irrespective of which method we choose, the frequency is not going to remain at 9.1.
So, like, let's say, for example, we find something else, let's say another method, and then the method is going to have higher precision, of course. That's what I mean, higher accuracy.
Mhm.
So that will I mean, like right now, as it stands, we have the 1 second, which is like roughly like let's say, I mean, a spin of the. I mean, I know all of this. I'm just trying to make it like in a human like language. So like, for example, you have like this 84,000 of it that is like a spin of the Earth for 1 day. And I mean, all of these things are so questionable. That's why I hate speaking so inaccurate. But all I'm trying to say is the duration of 1 second that we are measuring right now with the 9.192631770, is that going to be slightly also adjusted, or we're just going to define it better? And right now it's defined also to this point. We're just going to increase the precision, or we're going to just hop the accuracy as well. That's what I want to have
So
clear.
yeah, the accuracy is purely based on the definition,
Exactly.
right? Say, for example, right now, if you were to look at the accuracy of a rubidium clock, okay,
Mhm.
it can never be as accurate as the cesium clock because the definition itself is to do with the cesium clock,
Mhm.
right?
Yeah.
So, therefore, there will be an offset from that accuracy,
Mhm.
right?
I see. Okay.
Um, so when you define a new definition, either based on any other species, and it will definitely not be cesium, it would have to be, as I mentioned,
Yes, of course.
the other atoms,
Yeah.
or you would take a theoretical value as an ensemble of different kinds of clocks, right? Then also the accuracy is how close you are to that defined value. And in that process, in the second method, cesium would also be one of the clocks that will be contributing to um, meet that accuracy, right?
Yeah.
So it's not, see, for most of all these applications that I mentioned,
Mhm.
accuracy is not so important.
Yeah.
Stability is,
Yeah.
right?
Makes sense.
So as long as you stay where you are, that will only add an offset to the frequency in terms of the accuracy,
Yeah.
right? So for any of the applications that we dealt with here,
Yeah.
accuracy has almost no significant meaning.
Yeah. Yeah.
Yeah,
I mean, I'm more
except the
concerned where
UTC,
the
except
frequencies
the UTC.
translate to some measurement somewhere of a scalar, and then you're trying to go historically or something. That's where it becomes important. But as you said, most of the things we deal with, the intervals are comparisons of things that happen at the same time. They're all like differentials, basically.
That's right. Yeah, except the TAI.
That's right. Yeah, that's
Mhm.
right.
Yeah. Mhm.
All right, Hasham.
Yeah, I have one question. Did you look
Yes.
at molecular clocks?
Iodine clocks are molecular clocks, and acetylene, for example, that's also a molecular clock.
Yeah.
The optical
Okay.
clocks.
Okay.
Yeah.
Okay. Thank
Mhm.
you. Thank you.
Yeah. Cheers.
Anyone else? All right, another
Yeah.
just curious. Okay, we have Anik.
Yes. I
Anik,
mean,
you go good.
just in the ensembling, do you provide any? How do you provide the rating to the accuracy? How do you rank the accuracies? Is there any? Is there any reference that you add? Okay, AHM has the highest accuracy, and then followed by probably a cesium and then rubidium, and then how do you ensemble them? How do you generate an output based on those accuracies?
Yeah, nice question. So, um, depending upon how each clock is behaving at varying averaging time. Say, for example, a hydrogen maser is good from 1 second up to a day. And as you go towards 6 weeks and beyond, cesium beam clocks will start to outperform the hydrogen masers, right? So therefore, what sort of weighting factor we give at what time period? So this is how we design an ensemble, and yeah, I think that gives you an idea of how the weighting is done in an ensemble,
Yeah.
and therefore the accuracy it depends on which clock we give more weightage at what period of time.
Yeah, perfect. Makes sense. Yeah. Thank you.
Welcome.
Great. Any more questions? All right. Just one more, Fajesh. What was significant about 1023 that you call it GNSS Day?
Good. Nice question. See, each thing is having so much of history behind it, very hard to cover in 1 hour. So, yeah, nice question. 1023 is because the GPS or, Galileo and all these signals that we receive on ground, they're 1.4, anywhere from 1.4 to close to even in the S band, from L band to S band, if we take 1.4 to 2.5 gigahertz of frequency as we receive the signals, right? Now, if you have 10 megahertz, when you multiply the 10 megahertz to get to those frequencies, you can never have those. It will have to be those integer multiples, right?
Mhm.
So you cannot produce those different frequencies as you want. And therefore, instead of 10 megahertz as output from these clocks,
Mhm.
they use 10.23. Then you can formulate multiples of 10.23 in order to generate different frequencies.
Very
So
nice.
that's why it is sacrosanct. Yeah.
That's awesome. Very nice.
Yeah.
All right. Any more questions? If not, we'll again thank you, Fajesh, for awesome presentation and the extra 30 minutes. And we'll see everyone in 2 weeks by a talk from Steve Kolta from Meinberg about broadcast application engineering. So, that being said, thank you again and see you in 2 weeks. Bye, everyone.
Wonderful. Thank you all.
Yeah.
Thanks, Sam.